In this tutorial, we're going to perform a dynamic analysis on the same truss structure from the previous video. The truss will be loaded for a very short time duration, and we'll study the transient behavior of the structure. We're going to use Abacus Explicit for this procedure. The truss structure is fixed at one end with pin joints, which means it cannot move in the X or Y direction. However, it is free to rotate about the Z-axis. A concentrated force of 600 newtons is applied at one of the nodes for 0.01 seconds. We are going to use the dimensions from this schematic. We will use SI units where length is in meters. The radius of the truss members is 1 centimeter or 0.01 meters. The truss is made of steel with a density of 7.8 grams per centimeter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.3. In a static analysis, the inertial forces have little impact on the overall response of the structure. The standard general analysis performed in the previous tutorial did not include inertial effects. However, in a dynamic system, we know that the inertial effects will have a significant contribution to the structural response. We need to tell Abacus to capture these inertial effects. We do this using a dynamic analysis step. This can be achieved in Abacus Standard by specifying an implicit dynamic procedure, or in Abacus Explicit by specifying an explicit dynamic procedure. We're going to use Abacus Explicit as it's generally the best choice for problems with short dynamic response times or problems in which you are interested in the transient behavior. A lot of the steps we'll be following in the simulation are quite similar to the static analysis of the truss, so I'm going to go a little faster. I'm assuming you've already watched the static analysis of a truss video. We're going to start by renaming the model to truss structure. Then we're going to create a new part which is 2D planar, deformable, and has a wire base feature. We'll set the approximate size to 10 again. Once again, we sketch out the truss using the Create Lines Connected tool as we did before. We then use the Split tool to split up the segments into truss members. And then we use the Add Constraints tool to identify the truss members that are of equal length. And then we dimension it using the Add Dimension tool. We create the new material steel with a mass density of 7,872 kilograms per meter cubed. A Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.29. We then create a new section called Truss Section and set it to type truss. This section has the same steel material we just created and a cross-sectional area of 3.14 times 10 to the negative fourth. We assign the section to the entire truss. Then we move on to assembling. We instance the truss into the assembly as a dependent, which means the mesh will be on the part. This time we're going to create sets in the assembly. We're going to create two sets. The first one is the node on which the force will be applied, and the second one is the node at the extreme end of the truss structure where we're going to measure the displacement with time. To define a set, double-click on the Sets item in the assembly container. You get the Create Set window. Let's name our first set Force Point Set and click on Continue. At the bottom of the Sketcher window, Abaqus prompts you to select the geometry for the set. Click on the node on which we plan to apply the force, and then click Done. Repeat the procedure for the endpoint set. Now it's time to define the steps. We're going to create a new step called Loading Step and place it after the initial one. In the static truss analysis problem, we selected a static general step. This time we're going to go with a dynamic explicit one. We can type out a description, and we're going to set the time period to 0.01 seconds. So our load will be applied over a very short time duration. Notice that NLGEOM, which stands for nonlinear geometry, has been turned on by default. Dynamic explicit analyses are often carried on in models where large displacements are expected, and nonlinear geometric effects can become important. Turning on the nonlinear geometry setting tells Abaqus to account for geometric nonlinearity in that step. We're going to leave the field output requests to the default pre-selected variables, so we're not going to touch the field outputs container. However, we are going to define history outputs in the simulation. So expand out the history outputs container. You see that Abaqus has gone ahead and created a default called HOutput1. Right-click on HOutput1 and choose Rename. We're going to name this history output request Force Point Output. Double-click on Force Point Output, you get the Edit History Output Request window. We do not want the domain to encompass the whole model, but rather point to the sets that we have defined. So in the domain dropdown, choose Set, and then choose Force Point Set. Set the frequency to every n time increments where n equals 1. We're not interested in the energy in this model. We would like to measure displacements. So disable the energy variable from the outputs and instead expand out the displacement velocity acceleration container. We're going to choose UT, which stands for translations. Repeat the procedure for endpoint output using the endpoint set. Now we're going to create the loads. Double-click on the loads item. Let's name our load Force Pulse. It's going to be applied in the loading step, and it's a concentrated force. Recall that when we created the loading step, we gave it a time of 0.01 seconds. So that means our concentrated force will be applied to the truss structure for 0.01 seconds. Abaqus prompts you to select the points for the load. Notice the button Sets at the bottom right corner of the viewport. Since we've defined sets, we don't need to click on the node in the viewport. Rather, we can just click on the Sets button and pull up the set that we've already defined. Select Force Point Set. You can check off Highlight Selections in Viewport just to make sure you are selecting the correct set. And you see the force point node light up in red on the viewport in the background. Click Continue. In the Edit Load window, set CF2 to -600. CF2 is the force in the y direction, and our force will be applied downward, so that's a negative y direction. So we're applying 600 newtons in the negative y direction. Click OK. You see the force applied in our model. The boundary conditions are the same as the ones used in the static truss analysis. Double-click boundary conditions, set the name to pin, and apply it in the initial step. This is going to be a mechanical boundary condition, and choose displacement rotation. Since we'd use steps to select our load points, Abaqus assumes that you're also going to select sets for your boundary conditions. However, we haven't created sets for the boundary conditions. We plan to just select them in the viewport. So click on the button titled Select in Viewport at the bottom right corner of the viewport. Hold down the Shift key and click to select both nodes. In the Edit Boundary Condition window, we're going to constrain translation in the 1 and 2 or X and Y directions, but we're going to allow rotations, thus giving us a pin joint. We use the same meshing procedure as we did for the static truss analysis. We create the mesh on the part itself. We set the element type to a 2-node linear 2D truss. We seed the edges by number, assigning 1 seed to each truss member. And then we go ahead and mesh the part. Now we're ready for an analysis. We create a job called Truss Explicit Analysis job. We give it a description and set it to run a full analysis. We then right-click on Truss Explicit Analysis job and choose Submit to run the job. Once the job is completed running, we right-click on it and choose Results. You are now in the Visualization module. To view the history outputs, go to the Results menu and choose History Outputs. You see that U1, which is displacement in the X direction, has been saved for the force point set and the endpoint set, and the same can be set for U2, which is displacement in the Y direction. Therefore, you have 4 sets of history output. Let's plot the Y displacement of the endpoint set. Choose Spatial Displacement U2 in EndSet Endpoint Set and click on Plot. You see a plot of displacement with respect to time. Notice that the time is 0.01 seconds because that was the duration we set for the loading step. We also indicated when creating the history output that we would like it saved for the loading step. We'd like to save the data for this plot, so click on the Save As button. Let's name it Data for Endpoint, and click OK. Abacus creates an XY data object. Similarly, we can plot the Y displacement for the force point set, and we can save that as data for force point. Click Dismiss to close the window. Now that we saved both the plots as XY data, we can put them in a report. Go to the Report menu and choose XY. In the Select From option, choose All XY Data. This displays a list of XY data that we have gathered so far. You see that data for endpoint and data for force point have both been listed there, since we only just saved both those plots as XY data. Choose Data for Endpoint, then go to the Setup tab. Here we set a name for our output file. I'm going to call it endpoint xydata output.txt, which is a text file. And I'm going to uncheck the Append to File option, so that if this file already exists, we're not going to be appending to it. Abacus is going to delete it and replace it with the new file. In the Data section, for Write, check XY data, columns totals, and columns min-max. Switch back to the XY data tab. Make sure Data for Endpoint is selected. Click Apply. In my case, I had already created this file before. Abacus is prompting me to overwrite it, since I unchecked the Append to File option. So I'm going to go ahead and click Yes. You notice at the bottom of your screen, Abacus tells you the XY report was written to file. Repeat the process for the force point data. In this case, name the file forcepointxydata output.txt. And be sure to hit Apply to write the output file. And click OK to close the window.